Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 77, and it is entitled Equivalent Capacitance, EMF in Series and Parallel, and Half-Life and Rate of Decay. We'll focus on the first two parts of this three-part lesson, the last part not appearing on the AP Physics B exam. Half-life and rate of decay are interesting topics, and if you have the opportunity to study them at some later stage, I encourage you to do so. We begin with networks of capacitors. We first encountered capacitors in Lesson 67, these seemingly harmless charge buckets that at first glance appear pretty boring. And in this course, it is true that we don't do very much exciting with capacitors. So sign up for AP Physics C if you'd really like to see some dynamic capacitor capabilities. Because you've dealt with networks of resistors, to round out your education, you ought to know how to handle networks of capacitors too. And there are some questions that have appeared on past AP exams that involve them. And so we put these before you, capacitors in parallel and capacitors in series. First, let's recall what a capacitor looks like. This schematic illustrates the guts of a capacitor. If you've had a chance to see a dissected capacitor, then this first figure will look familiar to you. A common capacitor looks like a conductor-insulator sandwich that's rolled up inside a container. The conductor is connected to the outside circuit through terminals that extend from inside to the outside of the capacitor housing. Now, connect a bunch of these terminals together and the characteristics of the circuit changes. Exactly how it changes depends on how you make the connections. Let's begin with parallel connections. The terminals of the capacitors are wired together as they are in this diagram, with the negative and negatives wired together and positives to positives. Equation-wise, you'll recall that the charge on the capacitor is equal to the capacitance times the difference in potential. Where Q is the amount of charge stored on one plate of the capacitor, V is the potential difference between the terminals of the capacitor, and C is the capacitance of the capacitor. When capacitors are connected in parallel, the difference in potential across the battery and the difference in potential across the capacitor bank are equal. Each capacitor experiences the same difference in potential. You can see this when you color a circuit containing several parallel capacitors. The color difference across each of them is the same. Your authors derived the equivalent parallel capacitor formula, but I'll just write it down here. This right-hand circuit shows an equivalent capacitor CP for parallel that does the same job as these three capacitors C1, C2, and C3 together. The parallel capacitor CP is equal to C1 plus C2 plus C3. When the capacitors are connected in parallel, it's as if the area of the plates of the connected capacitors are enlarged so that more charge can be stored in the capacitor. The total charge, QT, is the sum of the charges across each of the individual capacitors. And we've already remarked that the voltage drop across each of the capacitors is the same. So these three equations are a characteristic of capacitors in parallel. It's also possible to connect capacitors in series, though in most practical applications you'll hardly ever see this. Theoretically, when capacitors are connected in series, the charge that leaves the plate of one capacitor migrates to the plate of the adjacent capacitor in the network, and the total amount of charge on each plate of the capacitor is identical to the charge that's on the plates of the other capacitors. I see I haven't left myself much room for talking about and writing about capacitors in series, so I'm going to move back up to the top and write some things down. When I connect capacitors in series and then connect those to the plates of a battery, what I'm going to see is that I end up with charge migrating from the plates of the capacitors to the plates of the adjacent capacitors. How much charge migrates? Well, let's take a look and see how this works. On capacitor C1, when charge plus Q appears on the left-hand plate of capacitor C1, then there's an equivalent amount of charge minus Q that appears on the right-hand plate. Where did that charge come from? Well, in the circuit, there's only one place it could have come from, and that was from capacitor C2. So what I end up with is a charge of plus Q that appears on the top plate of capacitor C2, which means that there's a charge of minus Q that appears on the bottom plate of C2. Where did that minus charge come from? Well, it must have come from the right-hand plate of C3. So I end up with positive charge appearing on C3, the right-hand plate, and negative charge appearing on the left-hand plate of C3. So the amount of charge that is on the plates of each of the capacitors is the same. Let's color the battery and the capacitors and see what happens in terms of the potential difference across each of the capacitors. Let's begin with the positive terminal of the battery and then the negative terminal. And now I see that I have to use intermediate colors of my Roy G. Biv scheme in order to color the other plates of the capacitors. So my next color for C1, I'm going to use orange. And going from capacitor C3, the next color that I need to use is blue. So what happens is the potential drop across each of the individual capacitors has to add up to the total potential drop across the battery. If you combine all these facts together and derive the equation, which your authors do, and I'm not going to in this particular lesson, you're going to see that the equivalent capacitance CS is related to the individual capacitance in a reciprocal sort of way. These three equations now characterize capacitors that are in series. And you'll notice that the combinations of capacitors in series look much like the combination of resistors in parallel. And in a similar way, the combination of capacitors in parallel look much like the combination of resistors in series. Let's take a look at a numerical problem. Three capacitors, C1 of 10 microfarads, C2 of 30 microfarads, and C3 of 20 microfarads, are connected in series with a 15-volt source. A. What is the equivalent capacitance? B. What's the total charge stored in the circuit? C. What's the charge stored on each individual capacitor? And D. What is the voltage across the 10 microfarad capacitor? Let's sketch the circuit first. Now let's use the series capacitor in order to figure out what the equivalent capacitance is. First, I'll sketch that circuit. And now let's use the series capacitance formula to figure out what the equivalent capacitance is. And we can put it in the numbers. At this point, you could substitute the numbers into your calculator, or you could get a common denominator, which is what I'm going to do. I find that the equivalent capacitance is just under 5.5 microfarads. Anytime you have these reciprocals adding in this way, you're going to find that the equivalent is going to be less than the smallest of the things that you're adding together. So my equivalent capacitance is less than 10 microfarads. That'll be true for resistors too. Part B. To figure out the total charge stored in the circuit, I'm going to use the capacitance equation. Q is equal to CV, where C is my 5.45 microfarads. So let me put in the numbers. The total charge stored on this equivalent capacitance is 81, nearly 82 microcoulombs. 82 times 10 to the minus 6 coulombs. In part C, we want to know what's the charge on each individual capacitor. Well, the charge is going to be the same on each individual capacitor. It's going to be the same as this nearly 82 microcoulombs. Finally, part D, the voltage across the 10 microfarad capacitor, I'm going to find using the Q equals CV equation. But now I'm looking for C of 10 microfarads, and Q is the 82 nearly microcoulombs. So I'm going to solve that charge equation for V1. And now I'm going to put in the numbers. And now I'll put that into my calculator, 8.82 volts. Now you might ask, why in the world would anyone want to connect capacitors in networks? And the reason is this, especially for parallel networks, because connecting capacitors in parallel allows the building of a huge capacitance, which can suddenly dump a bunch of energy into a circuit at the flip of a switch. Some applications need huge currents at a moment's notice, and a so-called capacitor bank enables such an application. applications including the operation of the Large Hadron Collider, or the LHC, at the European Centre for Nuclear Research, CERN, straddling the border between France and Switzerland. So much for capacitors. Now, let's go on and talk about sources of EMF in series and parallel. Why, might you ask, would someone want to connect batteries, the most common source of EMF, in parallel? Why would anyone want to connect batteries in series? Let's take these questions one at a time. First, batteries in parallel. One common place you'll find parallel automotive batteries is under the hood of vehicles using diesel engines. You can see two batteries in this vehicle, one on this side and one on that side. I currently drive a Dodge Ram 2500 pickup truck with a diesel engine. These engines require a lot of torque to get them started, and a single 12-volt battery would not supply the current needed to get the starter motor to turn the engine over, especially on a really cold day. So, under the hood, you'll find a pair of batteries connected in parallel. It's still a 12-volt system, and that pair of batteries supplies the current needed to crank the engine. Generally, batteries connected in parallel will have equivalent voltages, like the two 12-volt batteries under the hood of a car. It really makes no sense to put batteries of different voltages in parallel with each other. So, the voltage drop across parallel batteries will usually be the same. On the other hand, the current that's supplied by the network of these batteries is going to be equal to the sums of the current supplied by each battery. Both the batteries serve as charge pumps, and they boost the ability of the network to deliver current to the device requiring it. And now for batteries in series. Whenever you load a battery-powered device, such as a digital camera, as in this diagram on the right, or a flashlight, or battery-powered toy with more than one cell, you're connecting those batteries in series. These photos show batteries connected in series. When you do that, the total potential difference of the network is boosted. If you put four 1 1/2 volt cells together to power your radio, you've created a power source with a 6-volt potential difference. For batteries in series, the voltages add, whereas the current through each of the batteries is identical, because there's only one path for the current to follow. You would get a nasty shock from this array of 9-volt cells on the left, were you to grab both terminals with your hands. It might not kill you, but it just might. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 9-volt cells connected in series. 9 times 11 is equal to 99, almost 100 volts, and you would get quite a jolt out of that. Your authors don't provide any numerical examples with this topic, and so we're going to leave the subject here too. It's good to know how sources of EMF combine and what practical steps you can take to boost your current, i.e. connect your batteries in parallel, or to boost your voltage, i.e. connect your batteries in series. For now, that's it.